Do we have? Oh, there we go.
Hello, everybody. Hello, how are you? And welcome to our live solve. So, first of all, if you weren't with us last time, you can still watch them on YouTube. We actually have the recordings of the previous two there. But this is our third session that we're doing on the MATHCOUNTS state competition. So yes, we are going to do some math. We are starting now indeed. And again, I would like to emphasize that this is an official collaboration with MathCounts. So please do not just put these questions out there on the internet. They are copyrighted. Okay, so that's just a thing to be careful of. Well, with that, since this is the third one, you kind of know how the system works. We have this chat relay. If you happen to be in our Zoom meeting, send your messages to chat relay, and then we're going to see them. All right. So now the way that this always works is that, yes, I'll be here doing some of the questions. And in fact, I am in my studio today, so I will be able to do some of them. But the real highlight is not me. It's because we have two extraordinary people who are here as co-stars, co-hosts. I'd actually like to say a little bit to welcome each of them. So let's go in order of first name. So who would that be? Michelle, can you just say something so you take over the screen and I'll introduce you?
Hello, everyone.
Great. And this is Michelle. Michelle is terrific. She actually has a lot of experience with math. In fact, I also just saw her about a week ago at the Montgomery Blair Math Competition, where she was one of the people helping to volunteer as one of the people helping to run it. She goes to one of the top high schools in Maryland. And she also has done the University of Maryland Math Competition as well, where she was an honorable mention. But she does many other things as well. She also plays violin and volleyball and enjoys physics and coding. Now, I'd also like to introduce my other co-host, Vincent. Can you say something so you go on the screen?
Something so you go on the screen.
Man, that works really well. Okay, so Vincent, I actually had the chance to meet this summer because he was at the US National Math Olympiad training program. And I have actually gotten to stay in touch ever since then because of this program here. And he was actually a USA Math Olympiad silver medalist last year as well. And he's been an Amy qualifier since sixth grade. Amy is the second level high school math competition. He doesn't only do math, he also loves Rubik's Cubes. But we're here to solve some other kinds of problems. So we are going to today be working on the MathCounts state rounds, the target and the team. These actually officially require, no, they don't require, they allow the use of a calculator. And so, well, we might need to use a calculator here and there when the numbers get too messy. But with that, let's do this. Maybe let's do this where I don't start with the first question because I just did the whole intro and it'd be boring just to watch me. I think that it would be pretty cool to pop over to Michelle, are you good? I was hoping that your Rubik's Cube would be done by the time I called you.
Yes, I am good. My Rubik's Cube is done. Yeah, I drew it. Well, it's almost done. It's missing two lines. There, now it's done. But yeah.
Awesome.
And
So why don't you take over the first question then? And then we'll go you, and then Vincent, and then me, and so on.
Awesome. Sounds great. So our first question is, an arithmetic operation, plus, minus, times, or divide, is written in each blank in the expression 4 blank 3 blank 3. How many different values can result when this expression is evaluated? Now, this is a very, very interesting question because there's so many different options. But if you actually take a step back and think about all our options, there aren't really that many because we only have 4 possible operations and we only have 2 spots, which means that at most we have 16 different possible equations. And so from there, we can kind of just brute force our way through all 16 expressions and just see what we get. So let's go ahead and just write all of them. So 4 plus 3 is equal to 10. 4 minus 3 is equal to negative 2. 4 times 3 is equal to 36. 4 divided by 3 is equal to 4/9. Yeah, exactly, Jasper. So the reason we can't just say the answer is 16 because there are 4 different operations and 2 spots for the operations is because some of these expressions may actually end up giving the same value. And we're not asked for the number of different expressions, we're asked for the number of different values, which is why it's important that we make sure we keep track of all the possible different values it can be, which is why I'm listing them out right here. So far we have 4, and none of them have overlapped so far. So let's go ahead and continue on to figuring out if any of these actually do overlap. So next we have, so I started with doing just like all of them having the same operation. So plus, plus, minus, minus, times, times, divide, divide. And now I'm going to move on to operations where two of the spots are different. So one of them is 4 plus 3 minus 3, which is equal to 4. Another one of them is 4 minus 3 plus 3, which is also equal to 4. And so there we go. We have our first duplicate operation value in the sense that they all have the same result. And so even though there's two different operations here, we actually get the same value. So it's only counted once when we're counting the number of values. And we can continue. We can also do times and divide. We have 4 times 3 divided by 3, which is equal to 4. And 4 divided by 3 times 3, which is equal to 4. Yeah, so Skylar suggested 14. And that makes sense because we know that there are already 3 duplicates and 16 possibilities. So we know that the answer should be around 13. Though I think that in this case, it's not 14 because we already found 3 duplicates. And so it should be a little bit less than 13. In fact, I have a feeling that these are the only duplicates that we have. And I think it has something to do with the fact that when we do like multiplication and multiplication and addition, what we end up getting is a really, really big number. And if we do division and subtraction together, we end up getting a really, really small number. So for duplicate values, it should typically be in the form of an addition and a subtraction or a multiplication and division because then those two cancel out. And because they have because you can like switch the order of multiplication and division. Though I'm not exactly sure if they're the only values. I do have a feeling that they are. Vincent, do you have any ideas?
Okay, well, I guess we can continue trying out all of the possibilities since there doesn't seem to be a way to see if there's more duplicates that is faster than just trying other combinations. So now let's try the combinations with plus and times together and minus and divide together. So we'll try 4 plus 3 times 3. That's 4 plus 9, which is 13. Be careful to do the times first because that's how the order of operations works. And then 4 times 3 plus 3, that's 12 plus 3, that's equal to 15. So far, no duplicates. Let's try 4 minus 3 divided by 3. We'll do the division first. So that gives us 4 minus 1, which is 3. And 4 divided by 3 minus 3. This one's a bit more tricky because now we have fractions. This is 4 thirds minus 3. 3 is 9 thirds. So this gives us negative 5 thirds. So far, no duplicates.
Yeah.
And finally, yeah, as Jasper says, we'll do division and addition together and subtraction and multiplication together. Those are our final 4 possibilities. So let's try them and see if we get any duplicates. We'll do 4 divided by 3 plus 3. This is 4 thirds plus 3. 3 is 9 thirds. 4 plus 9 is 13, so this gives us 13 over 3. Definitely something we haven't seen before. Let's try 4 plus 3 divided by 3. This gives us 4 plus 1. 3 divided by 3 is 1, so this is 5. And the final 2 possibilities are with subtraction and multiplication together. So 4 times 3 minus 3, that's 12 minus 3, which is 9. And 4 minus 3 times 3, that's 4 minus 5. No, 4 minus 9, and that is negative 5. So other than those 4 4s we got, none of our other values were duplicates. So we have one value, that's all of the 4s, and then the 12 other ones that aren't duplicates with anything. There are duplicates, Sophia. The 4 possibilities where you have plus minus, minus plus, times divide, or divide times. And those only give us one different value. But the other remaining 12 possibilities give us 12 different values. So the total number of different values would be 12 plus 1, which is 13.
Yeah, I also came up with that. Actually, I was watching Michelle start, and I was also thinking there must be some nice way to do this. This is question number 1 on the target. But as Michelle kept going, I was like, wait a second, what's the pattern? I don't see any pattern. And then I decided to just do similar to what Vincent was doing, but I drew it like a table. So if I drew it like a table, the way to read this table is this is the symbol that goes in the first one, and then this is the symbol that goes in the second one. So for example, this thing would be 4 is in the plus and then plus. So it's 4 plus 3 and then plus 3. And then this thing here is in the plus and then the minus. So it's in 4 plus 3 and then minus 3 and so on. This is the only way I could think of to write the whole thing in a small way. But my brain was also swimming with getting confused as I was drawing this because I forgot which one was for which of them. The order matters. At first I was like, maybe the order doesn't matter, but it actually does matter. So, and it also got really weird once you got the fractions. So I actually do not know a better way than the brute force.
I think it's a really, really weird question. I bet you there is actually a better way to solve this. Just because if you were to ask me this question and give me 5 seconds to do it, I would probably guess 13 as well. Just because, well, I would assume that like 4 plus 3 plus 3, those values are all unique. But then that like since addition and subtraction are kind of commutative and you can switch them and we have 2 3s, that these would be the values that are duplicated. And they just so happen to all be 4, which is awfully weird. And so I bet you there is some really smart way of doing it. And yeah, and as someone said, the table is really, really smart. It's definitely a lot better than just listing them up and taking up way too much space. It's a very nice, concise way to write things.
Yeah, I just did it because I was watching you guys and I was like, oh no, I don't see any other way. I also should say I only highlighted the duplicates. So there is another 4 here, but I didn't know that 4 was the only duplicate. So I was going through with my highlighter and just blocking everything that I'd seen before. All right. With that, I think we should probably go to the next question. So Vincent, that would be you.
All right. So our second question is, the point P has coordinates m comma n, where m and n are integers. So P is a point on the coordinate grid. It is a lattice point. Suppose that P is reflected across the x-axis to obtain the point Q. Then the point Q is reflected across the y-axis to obtain the point R. So we're going to reflect across the x-axis, then across the y-axis. Given that the area of triangle PQR is 80 units squared, what is the least possible value of m plus n? So let's try first graphing it so that we can visualize this problem. Otherwise, it's going to be hard to make progress. So we'll have our coordinate plane. And this will be our x and y axis. So let's say point P is here. And it has coordinates m and n. Then if we reflect it across the x-axis, then we'll be here. We'll have point Q, which has coordinates negative m, n. And we'll reflect across the y-axis to obtain point R, which has coordinates negative m, negative n. And this symbol means the absolute value. So we're looking at what the absolute value of m plus n is. Note that it's not the absolute value of m plus the absolute value of n. If it was like this, it would be a different problem. So we'll have to be careful about that at the end. But we're looking for the area of triangle PQR. So the triangle PQR will look like this. And one thing that jumps out at me right away is that it is a right triangle. So its area will be 1/2 times the product of its legs. So what would that be? Well, this leg would have length 2n, because this point would be m comma negative n, and this point is m comma n. When we change from n to negative n, then we change by 2n. Yeah, good catch, Rihan. It is m comma negative n. So because we went from m comma n to m comma negative n, this side is 2n, and then likewise, for here, we go from positive m to negative m. So this side would be 2n. And now we don't really need the coordinate grid anymore. We just need integers m and n such that the side lengths are 2n and 2m. We have to be careful because m and n could be negative. There's nothing in the problem that prevents them from being negative. But as long as we keep that in mind, we should be okay. So if m and n are the side lengths of a triangle, how will we use the rest of the information to get our answer? Well, we have 2m, 2n, and the area is 1/2 times 2m times 2n, and we know that the area is 80 square units. So that means that 1/2 times 2 times 2, that is 2. So 2mn equals 80. So therefore, mn equals 40. So the product of the coordinates has to be 40. It could be positive 40 or negative 40. So what would the possible values of m and n be? Well, 40 is equal to 2 times 2 times 2 times 5. But a better way might be to look at what factors it has. So I see it can be 5 times 8, 4 times 10, 2 times 20, or 1 times 40. And the coordinates could be negative of those for each. So if it was 5 times 8, we could have a point at 5 comma 8, or we could have a point at 5 comma negative 8. That also works. Or we could have negative 5 comma 8, or we could have negative 5 comma negative 8. Any of those combinations work. If we had a 4 and 10, for example, we'd have positive or negative 4 or positive or negative 10, and so on. So let's look at the 5 comma 8 case first. In this case, if we want to minimize the value, the absolute value of m plus n, we want one of them to be positive and one of them to be negative. Because if they're both positive, let's say they're 5 and 8, then the absolute value of m plus n would be 5 plus 8, which is 13. But if one of them is positive and one of them is negative, as Ling says, they would sum to 3 or negative 3. And the absolute value of that is 3. So the best we can do in this case is 3. All of the other options have two numbers that are further away. So if we added them together, then that's going to give us greater than 3. If we subtracted them, it's going to give us greater than 3. So no matter whether we make them positive or negative or both, we're going to get something greater than 3. And we want the least possible value. So therefore, the least possible value of the m plus n's absolute value should be 3.
Yeah, I think that's correct. Let me check. Yes, that is right. I should say this is a pretty tricky question. I in fact, at first when I was looking at it, I was like, oh, m and n may as well be positive. It won't make a difference. But as you guys were thinking about it, I realized, oh, wait, m plus n can be subtracting. Nice. Okay, but once you figure that out, I think this question ends up being easier than the first question, assuming you figure that out. Okay, by the way, if you've never done these math counts problems before, once you're in the target round, these are where there are 2 questions at a time and 6 minutes to do them. And usually the first one is easier than the second one. So now I'm going to go to question 3, because I guess it's my turn. And this is supposed to be the easier of the pair. So let's see what happens. Oh, no, this is not easy. Okay, by the way, if you can tell, I haven't looked at these questions before. That's the entire point. So, right, what is this? I have to go and deal with how many Sundays there are. Oh, maybe that's not that bad. Okay, 2023. Ooh, I'm in a place where people like noisy cars. All right, so 2023, that's a non-leap year. So there's 365 days. Actually, this might actually be okay because I like to draw my calendar starting on Sunday. All right, so let's just go ahead and divide by 7 because we're just going to make all these rows of 7, right? So let's see. Maybe I can actually do this question. 365 divide 7. Maybe you guys already know this because you do math contests, but I forgot because it's been too long. Okay, times 2 is 14. 1. Oh, so there's 1 leftover day. That means that if I were to draw the calendar is going to look something like this. So here's the very, very first week of the year, 1, 2, 3, 4, up until 7. That's the very first week of the year. There's lots of these, and it goes until the the last full week of the year. And then it has 1 more extra. Does this seem reasonable to people? So there's going to be this one extra day, because if I draw out the calendar, it's going to go and then 1 more here. Well, of course, there are 52 weeks in the year. I guess we sort of knew that. But so it's 52 weeks in the year plus the 1 more day. So I think there's 53 Sundays. This is Sunday. So I'm coming up with 52 plus 1, which is 53. Okay, I did it. Anyone have anything to add, or else we'll just go on to Michelle for the actual question?
No, I think that was a wonderful way. I really like the way you drew the 1 through 7s. I thought that was very, very smart and very nice to explain. But now I'm a little bit nervous about this question. Okay, it's a geo question. So in the figure shown, the center of circle O is located on side PQ of square PQST. Given that PO is 2 centimeters, RS is 4 centimeters, and ST is 6 centimeters, what is the area of the shaded region? Give your answer in terms of pi. Now, whenever I see geo questions, especially whenever I see geo questions with weird, funky areas that I don't know how to deal with, like, for example, this area, like, I don't know a formula for that area. So when I see geo problems like this, my first thought is, let's try to split this weird, funky creation into shapes that I do know how to deal with. Well, I know how to deal with triangles, I know how to deal with squares. I also know how to deal with parts of a circle. So like a slice of pie on a circle. So let's go ahead and split my diagram so that I get slices of pies and triangles and squares. I think I'm going to draw my line like this so I get a nice triangle here. I'm going to draw another line like this so I get a nice triangle here. And then I'm left with a slice of pie and a very big square. So if I wanted to find the area of the shaded region, what I could do is I can find the area of my big square and then subtract from it 2 of my triangles. So those little rectangles, they might not be equal, but I'm just going to write this in this way for now for clarity. And then minus my slice of big pie. And now what I've done is I've broken up this really, really ugly shape that I don't know how to deal with into nice shapes that I do know how to find the areas of. So let's go ahead and do it. Well, before we find the area of these shapes, we do need to know a little bit more about them. So let's find the side lanes of things. Well, we know that PTSQ is a square, and so all 4 side lanes of the squares need to have the same side. And since ST is equal to 6, because QS is another side of the square, QR is also equal to 2, and OQ is equal to 4, and so on. And from there, what I can do is I can actually use the Pythagorean theorem to find what OR is. Because we know that squares have right angles here, we can easily find OR because we know the 2 legs of our right triangle. And applying the Pythagorean theorem, we get that OR is equal to 2 root 5. And look, OR just happens to be my radius of the circle. And the radius of the circle stays same all throughout the circle, which means that OT, which is the other radius, well, another radius of the circle, is also 2 root 5. And hey, look at that. I also have 2 known side lanes of my right triangle. So I can find the length of my other triangle. But wait, before I apply the Pythagorean theorem, I have the triangle right there, don't I? I have a 2 root 5 for a 2 triangle. And so I also know that with this triangle, it's also going to be a 4, 2, 2 root 5 triangle. And last but not least, knowing that this length is 4, we can find that this length is 2. Okay. And now to figure out the actual values of everything. We do know that the square is of area 36 because it has a side length of 6 each. So this is a 36 area. And we also do know the area of the 2 right triangles. In this case, they happen to be equal. So this is just going to be 2 times 4, which is 8. So the sum of these triangles is going to be 8. And now let's move on to our pie slice. Now, there is a little bit of nuance here because while I do know the radius of my pie slice, I don't actually know how far the angle is. And that's really important in determining how big a slice of pie is. Like, if you have a slice of pie that's like 180 degrees, that's like half the pie right there. Whereas if you had one that was only 1 degree, that's like barely a slice. So we have to figure out what the angle is. And luckily for us, we know that this is going to be an angle of 180. And because we know that these 2 right triangles are going to be the same, we know that this angle here is going to be equal to this angle here. But we know that this angle here is just going to be 90 minus my shaded angle, which means that my shaded angle plus my 90 minus the shaded angle is just going to be 90 degrees. So conveniently for us, the angle of this pie slice is just going to be 90 degrees, which I love because 90 degrees, isn't that like a perfect 1/4 of a circle? And so we know that this pie slice is 1/4 of the area of the circle, which is 1/4 times 2 root 5 squared pi. So now putting everything together, we start with our large square of area 36. We subtract out the two triangles, each with area 4, so minus 8. And we subtract out our 1/4 size of pi, which is 5 pi. And we gotta check the 36 minus 8 because we gotta simplify that. And that just gives us 28 minus 5 pi, which is our answer. Hopefully.
Yay! That's right. Random fun fact. If you do a math counts problem, the angles in the fractions of circles will probably be nice, or else you can't get the answer. So, of course, what Michelle did is the right way. She actually proved that it's 90 degrees. If you couldn't tell it was 90 degrees, you'd be like, well, it can't be 89 degrees. So it's probably 90 degrees. Somebody else asked, are these 30, 60, 90 triangles? Actually, they're not. They're not. These are not 30, 60, 90 triangles. So what Michelle did was the correct way to be careful with Pythagorean theorem.
Yes. I really like how math counts problems always give you really nice angles. I did solve a previous one, and at first I was like, how am I going to solve this question? But then I realized it was just a nice 45-degree angle. So,
Yes.
love that.
Cool. With that, I think, Vincent, why don't you take the next one?
All right. So the next one is the set of integers 1, 3, 9, 11, x has the same mean and median. What is the sum of the possible values of x? So the median could be any one of these values. This is a set with 5 values, and so the median is just one value. When the set has an even number of elements, you have to worry about there being 2 middle elements and taking the mean of those. But luckily, we have an odd number of elements, so the median is just the center element. So the possible values of the median could be, the median could be 1, the median could be 3, the median could be 9, the median could be 11, and the median could be x itself. So let's try to see if all of those are actually possible. So if the median was 1, well, then it would have to be the middle element. So that means the elements would have to use something, something, 1, something, and something. But that means that there has to be 2 elements that are less than 1. But we already know all but one of the elements. We know that 3, 9, and 11 are in the set. And we ran out of space. There's not enough space to fit all of the numbers on this side. And we have empty spaces here. So we know that 1 can't be the median. 1 can't be in the middle. So how about 3? If 3 is the median, then well, we have our 9 and our 11, and we have our 1 and our x. So whether 1 is greater than x or x is greater than 1, we'll see. We just need to hope that x is less than 3. So if we want the mean to equal the median, then let's just say it goes like this. Then the mean would be x plus 1 plus 3 plus 9 plus 11 over 5. And we want this to equal the median, 3. So that means that x plus, let's add up all of these numbers. 1 plus 9 is 10, plus 11 is 21, plus 3 is 24, over 5 equals 3. Multiply both sides by 5, x plus 24 equals 15. So therefore, x equals -9. So if the median is 3, then x equals -9. Let's put that off to the side and look at our next possibility. What if the median was 9? Well, if the median was 9, then our values are 1, 3, 9, 11, x, and we want 9 to be in the middle. So we have our 9, and we still don't know if 1, 3, 11, or x where exactly they fall, but we do know that 1 and 3 are less than 9. And so we'd better hope that our x would be greater than 9, because otherwise 9 wouldn't be in the middle. So let's say it looks like this. Then our mean would be 1 plus 3 plus 9 plus 11 plus x over 5. And we want that to equal 9. That means 24 plus x over 5 equals 9. 24 plus x equals 45. And so therefore, x equals 21. And this does indeed work. Our 9 is in the middle, and we have another candidate for x. X equals 21. Now let's look at the possibility. What if 11 was the median? And some of you have noticed that's actually not possible. But let's take a moment to see why. So if 11 was in the middle, then that means that 2 numbers are less than it and 2 numbers are greater than it. But we already know that 1, 3, and 9 are in the set. So this side is overcrowded. There's not enough space. So similarly to how we figured out that 1 was not a possible median, 11 is also not a possible median. So we can also forget about that possibility. So we just need to figure out the possibility that the median is x. So this one is probably the least straightforward, but it can still be done. So let's say the median is x, then 1 and 3 have to be less than it, and 9 and 11 have to be greater than it. The mean would be 1 plus 3 plus 9 plus 11 plus x over 5, and we want that to equal the median x. We'll multiply both sides by 5, we'll get 24 plus x equals 5x, 24 equals 4x, x equals 6. And this is indeed in the middle of 3 and 9, so this is another possibility. We've gone through all the possible medians, and so therefore we've figured out all of the possible values of x. But they're not asking for what the possible values of x are. They're asking for what the sum of the possible values of x are. Look at the problem again. What is the sum of the possible values of x? So we just need to add them up. -9 plus 21 plus 6. That's -9 plus 27, which equals 18.
Yes, that's correct. I was also playing with this at the same time. So yes, that's correct. As a fun fact, I mean, the one thing that a little tiny, it's not really a shortcut, it's just another way of checking your work. If you know that your median, or if you know the average of the 5 numbers is supposed to be x, then that means the sum of the average of the other 4 is also supposed to be x. So if the average of 5 numbers, one of which is x, if the average is x, then the average of the other 4 is x. This is like if your score at the end of the semester is like the average of all your scores, and on the final exam you just get the same score as your previous average, it doesn't change your average. And so this is sort of like what Vincent was doing. He was writing everything, dividing by how many there are. Oftentimes I'm just like, well, the sum of the number of the things is the average times how many there are. But again, what Vincent did was fantastic. Cool. Michelle, did you want to add anything, or are we all good?
No, I thought about it actually a little bit differently from Vincent. Instead of considering what the possible mediums were, I considered where x could be. And so instead of listing out the possible medians 1, 3, 9, 11, and x, I considered where x could be in like ratio in comparison to my other numbers. And from there, I was able to reach the same exact conclusion as Vincent, in which that the possible medians were 3, x, and 9 in this particular order. So yeah, wonderful job.
Yeah, terrific. Okay, I think I will then go on to the last, not the last question, the next question, number 6. Well, I said last because that's the second in the pair. Oh my gosh, what is this? All these words. Spencer writes a 2-digit number in each of the blanks in the sentence shown to make the sentence a true statement. Good for him. Both digits of each number are drawn from the set 1, 4, 7. Oh, so there's 2 2-digit numbers where you take the digits from 1, 4, 7, and Spencer is allowed to repeat digits and write the same number more than once. In how many different ways could he fill in this? Oh my gosh, there's 3 blanks. Okay. Whoa, okay. Some number is the arithmetic mean of something and something. Okay. So I guess the question is, how do I get arithmetic means to come out of this? Well, I see 1, 4, and 7 are equally spaced. Okay, so there's the one part of this, which is hopefully there's no trick question in here, because I'm looking at this and I'm saying, if I have 1, 4, and 7, if I could take the arithmetic mean of two-digit numbers by just arithmetic meaning the digits, that would be great. The problem is that's not true, okay? But let me give an example. So if I took the arithmetic mean of 71 and 17, if you arithmetic mean the 7 and the 1, so the tens digits, the arithmetic mean of 7 and 1 is how much? What's the arithmetic mean of 7 and 1? That's like the average of 7 and 1. Oh, cool. That's the 4, okay? And the arithmetic mean of the 1 and the 7, that is also a 4. Wait a second. Can I always get away with this? Oh, no, not always, not always. Yeah, it's annoying because, okay, in this case, I was like, wow, it worked. Let's do an example where it doesn't work. I wonder if I have a screen with, oh, I don't have one. Let me do an example where it doesn't work so well. So I'll use a different color for that. If I was doing 74 and 17 or something, if I did that, the reason this becomes nasty is because if you try to take the arithmetic mean of the 7 and the 1, that arithmetic mean is 4. And the arithmetic mean of the 4 and the 7, what's that? That's annoying. 4 and 7, the arithmetic mean is a fraction. Well, actually, what is it? Can anyone tell me what it is? So it's going to be a decimal. Let's say with the decimal. What's the arithmetic mean of 4 and 7? And it'll be a decimal. 5.5. So actually, this is a true statement, what I just wrote here. This is not allowed for the problem, but it is true. 45.5 is the arithmetic mean of 74 and 17. So it looks like we have a brand new way to take arithmetic means of two-digit numbers. Just arithmetic mean each of the tens and then the ones, sort of. Now here's where it breaks down. Suppose I wanted to do 47 and 71. Now if you try to do the same thing, when you arithmetic mean the 4 and the 7, what do you get? You get something terrible. Arithmetic mean of 4 and 7, what was that? Well, that was 5.5 again. So that means the very first digit, the tens digit, is 5.5. And then the ones digit is the arithmetic mean of the 7 and the 1, which is 4. That wasn't very nice. I wrote 5.5 and then a 4. Hold up. But actually, you see what? You see, it's sort of true. It's sort of true because it's 5.5 tens plus 4 ones, which is actually 59. Is the arithmetic mean of 47 and 71 59? Let me double check. 47, 71, 7 and 1 is 8. 1, 118. Yeah, it is. So it's correct. So what I'm trying to say is you can actually arithmetic mean two-digit numbers by arithmetic meaning the tens digits, arithmetic meaning the ones digits, and slapping them there. And if you ever have a decimal like a 0.5, you just carry it as a 0.5 times 10, which is an extra 5. Okay, I'm trying to figure out if this is going to help. Because what I was thinking here is, it looks like I can make, if I'm careful, and if I make it so that these numbers either use 1s and 7s only, or whenever there's a 4, the other one also uses a 4, then it should work. In the sense that, I mean, all of those will be things where when I arithmetic mean the place values one at a time, I'll always get nice whole numbers. Okay, so if I go and do this as an example, so let's write it as arithmetic mean of this. Wait. It was the other way around. This equals arithmetic mean. Let me write this way. This equals arithmetic mean of this and this. So now when I have this picture, I know certain ways with this nice trick now. If I ever use ones, fours, or ones or sevens, ones and sevens are very safe, because if I have a 1 and a 7, the 1 and 7 is going to give me a 4. Right. So if I use ones or sevens in these numbers, it's great. Like, I can do that. That's a 4. Okay. It's asking how many ways can we fill in the blank. So what I'm looking at down here is that inside these, using ones and sevens is very safe. Okay. Because if I arithmetic mean 1s and 7s, I get 4s, or I get arithmetic mean of 1 and 1 would be 1. Arithmetic mean of 7 and 7 is 7. So if I use 1s and 7s here, it's very safe. Very safe means always gets a number over here, which only uses 1s, 4s, and 7s. And so the number of numbers that use 1s and 7s over here, that is, I have 2 choices for each of the positions. So I have 2 choices for the first position, 2 choices for second position, 2 choices for third position, 2 choices for fourth position, which is 16 ways to do that. Then the next question is, what if I've got some 4s lying around? If I use some 4s, every time I use a 4, if I want it to look nice without this like extra 0.5 thing, and it looks like the 1s, 4s, and 7s, if I have the extra 0.5 thing, it just won't work. I'm just looking at this and I'm seeing if I do the extra 0.5 thing, I either end with a 0.5 or I have to randomly add a 5. And adding a 5 to any of the 1, 4, and 7 won't give you a 1, 4, or 7. So in this case, the only other things I can have are if I have a 4 in one position, that 4 forces a 4 in the other position because I only dare to average 4s against 4s. Okay, so I'll have 4 and the 4. I can have 4 and then the other 4. And then over here, I can have 1s or 7s, 1s or 7s. That's going to be okay because when I average the 4s, I get a 4. And then like this. And then over here, this is just the average of those 2 digits. So I have 2 choices for this and 2 choices for that. 4 ways. That was if there was 1 4. This is possibly not the most efficient way. I was like, that's if the 4 is in the front. I'll have another case if the 4 is in the back. And I'll have another case if it's 44 and 44, right? So it's either that way, or it could be something 4, and then something 4. That's another 4 ways. And then the last one is going to be 44 and 44, which is 1 way. Oh boy, now let's add everything up. 1, 4, 4, 16. I'm getting 25. I don't know if this is right. Do my co-hosts have ideas?
Well, there's actually another way you can think about it. So if you look at just the 10 digits, what are the possibilities for the 10 digits of the numbers that you're taking the arithmetic mean of? Like what 10th digit goes here and what 10th digit goes here? Well, you have either both 1s, both 7s, 1 7, 7 1, or 4 4. The only possibilities with 4s are if they're both 4s. And so if we just look at the 10th digit, there's 5 ways to do that. And a similar argument shows that there's 5 ways to fill in the 1s digit as well. So we have 5 options for the 10th digits, 5 options for the 1s digit. Everything else is determined from there. So we get 25.
Ooh, that's why it's a perfect square. Very nice. Okay, I like it.
Yeah, that was a really, really slick solution. Yes.
Okay, Michelle, I think it's you for number 7.
Yes, let's go ahead and hop onto that question. Oh, another geo question. I swear, I always get all the geo questions. Right triangle DEF has one side length of 2023 meters and is similar to the right triangle shown. What is the area of triangle DEF if all its sides have integers lengths? Okay. So we have this 40-75 triangle, and we know we want to like scale it really, really big, or possibly scale it really, really small so that one of its sides has 2023. But we also want to make sure that if one of the sides has length 2023, then the other sides are also integer side lengths. Before this is just like a lot of information to take in. So let's try to take a step back and try to see if we can simplify this triangle a little bit. Well, I noticed that 40 and 75 share a factor of 5, so I'm just going to go ahead and divide both of them out. And 40 divided by 5 is 8, 75 divided by 5 is 15. And this is a common Pythagorean triple of 8, 15, 17. And you can just get this by finding the square root of a squared plus 15 squared, which is just equal to 17. So now we want to scale this 8, 15, 17 triangle until one of its side lengths has a side length of 2023. But we want to make sure that whatever we're scaling this triangle by keeps the other side lengths integer side lengths. And what's really nice about 2023 is that 2023 just so happens to have a factor of 17 in it. I actually memorized this at the beginning of the year because math competitions tend to like putting the years of numbers into their problems. So it's always good to know the prime factorization of whatever given year it is. But the prime factorization of 2023 is 17 times 119. And so I know that if I scale this triangle 19 times its original size, then all my side lanes are going to be multiplied by 19. And because all my side lanes are going to get multiplied by 19, which is an integer, we know that the rest of the side lanes are going to stay integers as well, because the rest of them should scale accordingly as 8 times 19 and 15 times 19. 15 times 119. My bad, guys. Not 19, 119. But anyways, now we're tasked to find the area of triangle DEF. We could try to actually find the side lanes, and we could multiply them together and divide by 2 to find the area of the triangle. But that sounds like a really, really big number that I kind of don't want to deal with. So instead of trying to find the area of this really, really large triangle, let's just try to find the area of this triangle. Well, this triangle is just going to have an area of 8 times 15 divided by 2, which is equal to 60. And we know we want to scale this triangle such that each side lane is 119 times its original side lanes. And when I scale a length by 119, what I'm really doing is I'm scaling the area by 119 squared. And you guys can kind of visualize this as if I have a 1 by 1 square, that's an area of 1. But if I increase the lengths by 119, imagine that's 119, my new area is going to be not 119 bigger than my smaller area, but 119 squared. And so similarly, I want to scale this by 119 squared, and I get 16 times 119 squared. And we could actually solve this with 60 times 120 minus 1 squared, but I think I'm just going to leave this for the calculator to do. And so we get 16 times 119 times 119, which is equal to 849660.
Yeah, I was actually going to comment right before this question. I was like, man, we did this whole target round without using the calculator yet. And then as soon as I saw this question and I saw what you had to do, I was like, well, I take that back. The calculator is the fastest way to do this. Cool. Vincent, I think you're next, but I see you also put the 2023 factorization on your screen. Maybe it's good to mention that.
Yeah, it turns out you don't actually have to know the factorization of 2023, but it is good to know. If you didn't know it, here's how you could approach it. We know that it's an 8, 15, 17 scaled up by some amount. So we want to see which of those sides becomes the 2023. Well, if the 8 became the 2023, well, 2023 is not divisible by 8. It's not even, so there's no chance. So if this side were to become the 2023, then that's going to make the other two sides not integers. So we know that's not an option. If the 15 were to become the 2023, similar problem. Obviously, it's not divisible by 15. It's not divisible by 5. So there's no chance that it's divisible by 15. And so again, these will not be integers if that becomes a 2023. So the only option then would be for the 17 to become the 2023. And in that case, if we didn't know the prime factorization already, we could simply divide that by 17. But it is good to know the prime factorization of the current year if you're doing a lot of math competitions, because a lot of problems, like Michelle mentioned, a lot of problems will use the prime factorization. This year's prime factorization is especially interesting because we've got a bunch of relatively small primes in there. We've got 2 17s and a 7, which can make for some nice problems.
Cool. The most important year to memorize the prime factorization for is when the year is prime, because that would take you a very long time to test the prime factorization on the test.
That's true. What is our next prime year?
That's a good question. Vincent, do you know?
It is 2027.
Fortunately, you will be out of school by then.
Well, slightly unfortunately, because if I wasn't, then I'd be able to use it and I'd save, I don't know, a couple seconds.
That is true. That is true. Although actually you might be a senior in college by then, and then you can use it to make math contest problems for other people.
That's true. But just for the sake of all the little math competition people, please do not make a question asking what is the prime factoration of 2027? Because you would cause a lot of pain and suffering for them.
That is true. Okay, Vincent, I guess you're the next one. Also, I think you're number 8. The hardest question in the target round. We'll help if we need.
All right. The sequence A1, A2, A6 is a non-constant geometric sequence of positive integers in which each term is less than 2023. What is the greatest possible value of the sum of those integers? So we have A1, A2, A3, A4, A5, and A6. 1, 2, 3, 4, 5, 6. And there's no sneaky things with them possibly being negative or possibly being all of the same. So non-constant means not all of the terms are the same. So we couldn't have something like 5, 5, 5, 5, 5, 5. That's not allowed in this problem. They all have to be different, or at least some of them have to be different. But if some of them are different, then all of them will be different because the ratio between each term must be not equal to 1. So we could try ratios of 2, of 3, of 5, but actually we have to be careful because we can have ratios that aren't integers. And here's why. Let's say we started out with 32. What if our ratio was 3/2? Well, then the next term would be 32 times 3/2, which is 48. After that, we'd have 48 times 3/2 is 72. And then 72 times 3/2 is 108. And we keep on going. And hey, all of the terms are integers, even though our common ratio wasn't an integer. For those of you who don't know what a geometric sequence is, it's a sequence in which we get it by starting with a number and then we multiply it by a certain number called the common ratio, and we keep on doing that until we reach the end. So in this example, the common ratio was 3/2. So we actually need to look out for common ratios that aren't integers. Because at first you might say, oh, all of the terms are integers. That means the ratio must be an integer, but it's actually more complicated than that. So what are the possible common ratios? Well, we already tried 3/2. So we'll put it over here. 3/2 works. Any integer will work because as long as it's positive. If it's negative, then that violates the problem because the problem says they have to be positive. So any integer works. Let's try 4/3 next. Let's see if we have enough factors for that. So if we try 4/3, what's the effect of multiplying by something like 4/3? If we start with an integer, let's say it's 2 to the a times 3 to the b, and we multiply it by 4/3. Well, that's the same as multiplying by 2 squared over 3, which would give us 2 to the a plus 2 times 3 to the b minus 1. And in this case, we would want our final term to be an integer. So our first term has to have a b of at least 5. So the smallest possible value that works is 243 because 3 to the 5 is 243. Each time we multiply by 4/3, we're going to decrease this value by 1. if we write 243 equals 2 to the 0 times 3 to the 5, each time we multiply by 4/3, we're going to increase this by 2 and decrease this by 1. So let's see what happens. We'll start with 243, multiply it by 4/3, and we'll get 243 times 4/3. That's 324. 324 times 4/3. That's 108 times 4. That is 432. And the numbers are getting pretty big. But let's see what happens. 432 times 4/3. That is 1,290. No, not 1,296. 1,728/3. And it's 648. And it seems like if we keep on going, we should be less than 2023, but just barely. Okay. It should be 576, actually. So yeah, at this point, it's starting to get a little bit difficult to do the computation. And then if we multiply 576 by 4/3, we get 768. And we multiply that by 4/3, we get 1,024. So the terms are less than 2023, so that's good. Yeah, Sophia, maybe we do need a calculator because it's only going to get worse from here. So we'll keep this in the back of our mind. We know that 4/3 works. What if we started with something different? What if we started with 2 times 243? We can start with any multiple of 243, and everything else will still be an integer. But then this term will be twice 1,024. That's 2,048. And that's above 2023. So we know that we couldn't start with twice 243. That's not going to work. What if we tried another common ratio, like 5/4? It seems like we want our common ratio to be as low as possible without being 1. Because if our common ratio is really high, like, for example, let's say it was 4. Let's say we started with 1, 4, 16, 64, 256, 1,024. We're constrained by how big our highest number is. But if our common ratio is really big, then if we want to find the greatest possible value of their sum, these numbers in the front, they're not pulling their weight. So we want a common ratio that's closer to 1 so that all of the numbers are actually pulling their weight. Something else to notice is if we use a common ratio that is smaller than 1, then that's as if we're doing a common ratio that's larger than 1, but just in reverse. For example, if our common ratio was 3/4 and we started with 1,024, then our sequence would be 1,024, 768, 576, 432, 324, 243. And that's just our 4/3 sequence in reverse, which makes sense because multiplying by 4/3 is just multiplying by 3/4 in reverse. In other words, multiplying by 4/3 in reverse would be dividing by 4/3, which is the same as multiplying by 3/4. So because common ratios that are smaller than 1 are kind of the same as common ratios that are larger than 1, just giving us a sequence in reverse, we can just look at common ratios that are larger than 1. So let's look at our next option, 5/4. If our common ratio was 5/4, what does multiplying by 5/4 do? Well, let's say we had a number 2 to the a times 5 to the b. If we multiplied that by 5/4, that would give us 2 to the a minus 2 times b to the times 5 to the b plus 1. And so if our first number was something, then we would want a to be at least 10 so that we could subtract 2 from it at least 5 times and still get something that's an integer. So our starting number would have to be some multiple of 1,024. Then we'll multiply that by 5 over 4. We get 1,280 if I'm doing the mental math correctly. Let's actually double check it. So 1,024 over 4, that is 256 times 5. Okay, yeah, that is correct. So now let's multiply it by 5 over 4 again. Then we should get 1,280 over 4 times 5. That is 5 times 320, which is 1,600. If we multiply that by 5 over 4 again, we get 2,000, and it looks like we're in trouble because we want the greatest term to be less than 2023, and we're already really close to that. If we multiply 5 over 4 again, we get 2,500, and now we're really screwed. Now we know for sure that this won't work. And so whatever we do here, we're going to end up with something that doesn't meet the conditions of the problem. And if we try multiplying by more complicated fractions, 6 over 5, 7 over 6, in the hopes that our common ratio is closer to 1, we're just going to have even bigger numbers. And that's not going to help us. 5 over 4 was already too big for us. So we're not expecting these numbers to be doing us any favors. So we know that if the common ratio is an integer, we have a lot of freeloaders, a lot of small numbers that aren't really pulling their weight. So of the sequences we found, the 3/2 and the 4/3 look most promising. So I have the 4/3 up here. Let's write the 3/2 again. So if we multiplied by 3/2 the whole way, we would have something like 32, then 48, then 72, 108, 162, and 243. So we can multiply this by any number and still get a valid sequence. There's a lot to wrap your head around in this problem, so don't worry if you're confused. We're basically trying to find geometric sequences, that is, sequences that start with a number and then are generated by multiplying by some other number. So in this example, we started with 32, and multiplied by 3/2 the whole way, and that's how we generate our sequences. And we're trying to find the sequence where all of the numbers are less than 2023, and the sum of the numbers is as big as possible. The most you can multiply by, yeah. So let's try to see what the most we can multiply by is for this sequence. We're allowed to multiply by some number because geometric sequences do well with multiplication. Like if we multiplied all of these numbers by 2, like this, for example, we still satisfy the condition for whether something is a geometric sequence. We start with a number, and then after that, we're multiplying everything by 3/2. We're multiplying everything by the same number each time. So if we want to see what the maximum we can multiply by is, well, that's going to be constrained by our 243 here. We don't want that to exceed 2023. So I saw someone in chat say the maximum we can multiply by is 8, and that seems right to me. So let's check it. 243 times 8. That is 1944, which is less than 2023. Now let's try 243 times 9. That is 2187, which is larger than 2023. So multiplying by 9 is not going to work. So the greatest we can multiply by is 8. So we'll just say 8 times all of this. Now, we want to find the greatest possible value of A1 plus A2 plus A3 plus A4 plus A5 plus A6. And so we'll see which one of those is greater. So let's first try the top one, 243 plus 324, and so on and so forth. If we add those together, we would get 3367. And you would just do that by putting it into your calculator. And then if we wanted to find the sum of the bottom one, well, we could find this inner sum and then multiply it by 8. So once we find this sum, multiply by 8, we get 5320. We want the largest possible value, so 5320 is going to be our answer.
Yes, I think that is correct. This is interesting. Actually, I'll say the benefit of watching somebody else do it is then I have some more time to think about it. I did see somebody say, how can you do this in the time limit of math counts? Let me just make a few comments about this. I was supposed to do the next question, but we're over time. So unfortunately, this will be the last question that we do. However, I did see that there's a way to know about like what's the biggest prime number you'll see in the prime factorizations. One of the most interesting things that I didn't actually think about when I was in school is that if you take a geometric series, which is all integers, and you prime factorize it, then the powers on the primes are an arithmetic sequence. So this is a nice fact. Like, so here is the geometric series. This is actually the one that Vincent was doing, but I was writing it as prime factorizations instead of as the actual numbers. So if you have this is a sequence of 6 numbers. And the reason why they have a common ratio is because if you go from 1 to the next one, I always times by 2 and divide by 3. No, other way around. Divide by 2 and times by 3. That's why the exponent of the 2 drops by 1 every time, and the exponent of the 3 increases by 1 every time. So then my numbers are actually all going to have the form where you got like some 2s and some 3s, maybe. I don't know what my prime factors are yet, but whatever the prime factors are, they are either constant power, like the power doesn't change, or the powers move in some arithmetic progression, like getting bigger or getting smaller. These are the two interesting ones that intuitively I also thought would be nice because they're kind of going against each other. There was this notion of not pulling enough weight, is something that Vincent said. But the first thing I did is I went and said, what kind of prime numbers would I even be able to see? Because if there's a 5 anywhere in this, then I would have some term that has a 5 to the 5th power, which is too big. That was the key. So if I took 5 to the 5th power, that is too big. So that's how I know that in this entire problem, the common ratio doesn't have a 5 in it. If there's a 5, the 5 is only as the constant that you multiply everything by. That's this times 8 thing. We were both doing the same times 8 thing, both Vincent and this technique. So then the game becomes, all right, so I can have 2s, 3s, or 4s. 4s are 2 squareds. So that means that whatever my numbers are in the arithmetic sequence, they will be having some 2s, having some 3s. The 2s and 3s might be arithmetic progressions that go in some various orders, but the 3's arithmetic progression is only allowed to go by +1 or -1. Because if I went by 2s, then one of the terms would end up being like 9 to the 5th, which is too big. So the key was I'm only going to be able to go up to 4 to the 5th, because that's still underneath the 2023. So then I just started to go and say, well, how can I do it if I had 2s and 3s moving in opposite directions? The only way to do that would be if the 2s were, just as 2s, or if the 2s were as 4s. But moving in opposite directions, these are the only two possibilities. And then I wrote those out and I said, well, what's the biggest thing I can scale it by? The way you got to 8 is what you guys did, which is take 2023 divided by the biggest number. Or I could be this. And this is if the 2s are growing by 2 every time and the 3s are dropping by 1. And this you can't multiply by anything, because if you take 1024 times 2 is already too much. And then the other options would be there's no going in 2 directions. The other options would be either it just goes by, the common ratio just has 2s or just has 3s or just has more 2s. And that was my second screen's worth. It was that either the common ratio is 2, meaning that the things are 2 powers of 2 all multiplied by the same number, integer. And it turns out that integer would be 63. Or it's like they're powers of 3 and then multiplied by some number, or they're all powers of 2 squared and then multiplied by some number. But then when I looked at these two, I said, well, this one is just definitely worse. This is a times 8, it has a 243, and that's just definitely worse than this one, which is a times 8 and with a 243, because there's bigger numbers there. So then I said, I don't even care about that one. Similarly, this one is just worse than this one. So then I just started adding them up. I was like, what's that? What's that? And what's that? And I guess that's how I came to the answer. But it was inspired also by hearing Vincent, because I actually didn't think of the 4s. At first, I just did this with 2s and 3s, and I was like, oh, great. It's just 2s and 3s and nothing else. But you have to also be careful that 2 squared to the power of 5 can also still be under 2023. So I think this is, go on, Michelle.
No, I was just going to say that I thought this was a really, really cool problem. It's very fun seeing. So if you guys don't know, in the background, Professor Lowe is writing out his solution, and it was really cool to see hear Vincent's solution while watching Professor Lowe's solutions while trying to solve my own at the same time. It was like an influx of ideas. So yeah.
Yeah,
Awesome.
it's actually a lot of fun for us in this room because we actually just are watching each other solve the problems at the same time. Yeah, with that, unfortunately, we are over the time. So let me just quickly pop a little code on the screen. So yeah, we're unfortunately over the time. And so hopefully you guys had some fun. We actually also had a ton of fun. In general, with all of these live solves, we love doing collaborations, official collaborations like this with the organizations that put the questions up. And if you like these, you're always welcome to join us at future sessions as well. These are actually, we also have a newsletter we put out every 2 weeks, which will always have announcements of the next time that we do anything fun like this. I see some people want another hour. I'm so sorry. I personally actually have to run off because I also have an appointment I need to go to. I have a call I need to go to. And so unfortunately, we're at the end of today. We managed to finish the target round. If you like these questions, join Math Counts. It is how I got interested in math way back in the day. Great organization, great contest. Thank you, everyone. Good night. Bye-bye.
Yay, we're done.
Yes.
So many people want more.
Yes, it's a shame we